In today's lesson, we are going to analyze how we can take limits analytically. We will take a look at properties of limits, as well as what to do when the value you are trying to take the limit as x approaches is undefined. First, what we want you to notice here in this box is that if we see a sum, difference, product, or quotient of two functions within a limit expression, we can separate those two functions and evaluate the limit individually. So for example, if I were to give you the limit as x approaches c of 2x, then we could divide this into the limit as x approaches c of 2 times the limit as x approaches c of x. In part 1, we are given three different values for the limit as x approaches 2 for function f, g, and h. What we are going to do in examples 1, 2, and 3 is use the properties above and simplify with the given information. In example 1, I see that I have 4 times f of x minus g of x, and I know that I can separate all of these and evaluate individually. So I can say that the limit as x approaches 2 of 4 times the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x. Now we learned the other day that when you take the limit of a constant, regardless of what x value it is approaching, the value is always the same. So the limit of 4 as x approaches any number is always equal to 4. I can then go ahead and plug in the other two limit values that were given to me in the beginning of the problem, and plug in -3 and 5, and I get that the overall value of the expression is equal to -17. Even without knowing what the function f and g are, we are still able to evaluate the limits because of the information that was given to us. Pause the video and try the next two on your own. In example 2, when we break up the limit of the products, we get the expression that I have here in purple. Notice that each step of the way I need to write the limit as x approaches 2. That is all part of the notation. Now the first term, limit of x as x approaches 2, this is a linear function which we know to always be constant, so I can just plug the value of 2 straight in to evaluate, and that is how I get the value of 2. The other two values of 5 and 6 are given to us in the original problem. Multiplying them all together, we get the value of 60 for the given expression. In example 3, we break up our quotient and difference of our limits as we see here. By doing a substitution of our given values, we see that we have -3 divided by 6 minus, and then remember, whenever we take the limit of a constant, no matter what x value is approaching, it always equals the value of the constant. So -3/5 would be our limit value here. It's going to happen where there will be limits that you cannot simply plug in. In this problem here, we have the limit as x approaches 1. Now if you look at the given problem, 1 is undefined for this expression. I cannot plug in 1 because the denominator is equal to 0. However, that does not mean that the limit automatically doesn't exist. It just means that you need to work a little bit harder. And in order to evaluate these limits, you're going to have to rewrite or simplify the function so that you can directly plug in the given x value. You will know that this is necessary because if you try to plug the x value in directly, the function will be undefined. Examples of things that you can use to help with this would be factoring, rationalizing your denominator, using a conjugate, and canceling. If we refer to the problem that we have here, we can see that if the numerator is factored, we end up with the expression x plus 2, x minus 1, over x minus 1. And in its reduced state, the common factor x minus 1 can be canceled. So now what we have is we have a linear equation, y equals x plus 2, that has a hole or a point of discontinuity when x equals 1. So this would be why the x value of 1 couldn't be plugged in from the beginning. However, now that we go to evaluate our limit, the limit as x approaches 1 of x plus 2 is going to equal 3. And what that tells me is that my point of discontinuity occurs at 1, 3, and I can see on my graph that it will look like this. And this is another example of our rational functions where a common factor can cancel, leaving us with a point of discontinuity. In this problem here, we cannot directly plug in 9 because the denominator would be undefined. When you're trying to think through strategies of what to try, the first thought is to multiply by the conjugate. However, that's not really going to help you do anything for the denominator. What I would suggest instead is focus on the denominator and ask yourself, how can I get rid of that 9? And even though in Algebra 2 we didn't focus on factoring with radicals, looking at this is a great example of a difference of two squares. It's a difference of two squares where if you think about the x as a perfect square of the square root of x, we could factor x minus 9 into radical 3 plus 3, radical 3 minus 3. And when we do that, we can see that I'm actually going to be able to cancel off my numerator, and now I get an expression which I'm allowed to plug in my 9. Here's what that's going to look like. We'll have the limit as x approaches 9 of 3 minus radical x over radical x plus 3, radical x minus 3. Now my numerator is opposites with the radical x minus 3 factor, so they can cancel, leaving us with a negative 1. Now my expression is limit as x approaches 9, negative 1 over radical x plus 3. So I've taken the same problem and I have manipulated it. And after the manipulation, I can now plug in 9. So we can plug 9 in and we can directly evaluate our limit. Notice that each step of the way, I am constantly keeping the expression limit as x approaches 9. It's not until the very end when I actually evaluate the limit that I get rid of that part. So I now see negative 1 over 3 plus 3 or negative 1/6 as my answer. In example 5, my problem here is that I have an x in my denominator. And the only way that I can cancel off this x is if I can somehow get the x freed from my numerator, which is currently stuck in a radical. So what I'm going to do is I'm going to try multiplying both the numerator and the denominator by the conjugate of the radical that I see in the numerator. And we should remember from our Algebra 2 days that when you multiply by the conjugate, our difference of two squares properties make it so that I no longer have these radicals. So the simplified expression will give us limit as x approaches 0 of 5 minus the quantity 5 plus x all over 2x parentheses radical 5 plus x. Now I'm going to suggest that you wait to distribute the denominator because you may not even need to. It's possible that the x is going to cancel away, and if that happens, then there's no reason for us to waste time distributing and making the problem look messier. So in our numerator, this simplifies to give us 5 minus x, and the 5 minus 5 cancels. So now what I see is the limit as x approaches 0 of negative x over 2x parentheses root 5 plus x. And we have freed the x, and the x can cancel away. And we are now left with an expression where we can directly plug in x equals 0 to evaluate our limit. So if we go ahead and plug in our 0, we are then left with negative 1 over 2 times radical 5 plus radical 5, which gives me 2 radical 5. And final answer, negative 1 over 4 radical 5. If we finish that by rationalizing, we get negative radical 5 over 20. In example 6, the obvious choice is to go ahead and try factoring both of these polynomials. The numerator is something I would factor by grouping because it has 4 terms, and the denominator I can easily factor via trinomial rules. After factoring, we can see that the common factor x plus 2 can cancel, and we now have an expression where I'm allowed to directly plug in my negative 2. Again, our entire goal throughout this whole process is if I am not able to directly evaluate the limit, what can I do to change the problem so that I can directly plug in that x value? So now that I can, we go ahead and plug that in, and we can simplify to evaluate our limit. 4 plus 5 is 9 over negative 8. Example 7 is a limit that we are going to have you memorize. You'll learn more about this next year, but for right now, we want you to know that the limit as x approaches 0 of sine x over x equals 1. All the time, every time. And we're going to use this rule to help us finish off example 8. In example 8, we see some constants that we can go ahead and separate using the rules that we started the lesson with. First, I'm going to suggest that you separate this into two fractions, giving us the limit as x approaches 0 of 2 sine x over x minus the limit as x approaches 0 of 3x squared over x. The reason why we want to go ahead and do this is because I now see this sine x over x that we just talked about a minute ago in example 7. If I further divide these limits and rewrite them with the product rules, I'll see that I have the limit as x approaches 0 of 2 times the limit x approaches 0 sine x over x minus limit x approaches 0 of 3 times the limit as x approaches 0 of x, because we were able to reduce one of those x's. And now we go through and we just plug in all these individual limits. We will have 2 times 1 minus 3 times 0, giving us a final answer of 2. And that's all.